So, diving right in, I wanted to give a quick course overview about what we're up to this semester before jumping into our first lecture, which is kind of more of a review. So, we'll start a little bit slower. But first, what is pre-calculus about, or what we call functions 2? So, we're going to review the basics of functions, and then we're going to look at how we can combine and transform functions in general, and then apply that to these new families of functions, so exponential and log functions. So these are things that grow exponentially, as you might have heard before, which means in proportion to how much of something you have. So the rate of change is in direct proportion to the amount of something. So you can think of like populations, even temperature. There's exponential is a huge field and family of functions, and logs are their kind of counterpart. Things that grow logarithmically are things that spike at first and then grow. And this is actually kind of in the wrong spot, like this. Things that spike quickly with growth and then kind of taper off over time. So one way to think about this, I have a small child now, is the way kids learn numbers. They can learn 0, 1, 2, 3 very quickly, the difference between those things. But then the difference between 5 and 10 is that's pretty gradual, that progression. So we have a logarithmic just progression of our understanding of numbers, our own number sense. Then we'll move into periodic functions. Periodic functions are things that oscillate. So anything that has a repeated pattern, which is, a ton of different things. If you're moving into electronics, we're talking about signals. We're talking about the tides. We're talking about temperature fluctuations of biological organisms. So this is another huge field of families of functions. Those are kind of the main ones we'll look at. We'll also look at rational functions, which are not listed here. Things that are ratios. So there's like average cost functions, concentration types of functions. What you've studied before are probably power functions, linear functions, polynomials, things like that. And so we're extending this kind of library of behaviors that we can model using mathematics. Some of the key things we'll be doing are using the 4 perspectives, which if you've taken classes here at FLCC, you know pretty well, which are, verbally describing a function with words, using tables, using formulas or algebra, and graphs. And really the key a lot of times when we get stuck working with functions is and I'm going to say this now, I'm going to say it a lot. You're probably stuck in one of these perspectives. And if you move to a graph or you look at a table or something like that, from whatever perspective you're looking at, the other ones will offer you insight into the problem. Okay, this happens a lot more than you think it does. So remembering to switch perspectives, and we'll be trying to embrace all 4 as we move through the course. And then at the last part of this class, we're going to look at limits, which are considered to be the underpinning to calculus. But we'll be weaving this notation throughout the course a little bit. But really, this is a key idea in calc that you're going to need. So all of these things are really in service of preparing you for calculus. I know not all of us are going on to calculus. And all these things have their own value, but it is one of the major outcomes of this class to get you ready for Calc 1, Calc 2, and beyond. All right. So without further ado, that's what we're up to this semester, finishing out this library of functions and seeing how they play with each other. And so let's dive in now to reviewing some important concepts that we'll need all semester long, which are the domain and range of functions. Okay. So these might ring a bell, they might not. That's okay. So what are the domain and range of a function? Well, if you think about it as a set and a function is a rule, in general, a function takes from the domain and maps to the range. Okay. So the domain is the set of all possible inputs to a function. And the range is the set of all possible outputs. So first, let's work through these 4 perspectives on domain and range. So we have these different notations that I'll show you how to describe the set. Okay, so the first one we have up is a description of a function. The cost of a rental car is a function of the amount of miles driven. So we want to know what's the domain and range of this function. So what are some acceptable inputs for this? Well, remember the cost of the rental car, let's call that C, is a function of the number of miles driven. Let's call that M. So we could say C is the output of the function f of m, where m is the input. So we might actually mark this in here in case we're feeling rusty. All right, and f is the rule or the function. Okay. So what are the possible inputs here then? So that means what are possible amounts of miles driven? Well, it's helpful to kind of think about what's not allowed, right? So what's not allowed would be negative miles driven. That wouldn't make sense, right? Taking miles off the car. It's illegal. So so you can't have negative miles. So, you know, we could say it can't be negative. Can it be, you know, infinite? Maybe. I could see a case being made for that. Could it be like infinitely positive? You could drive this thing until the end of time? Probably not. There might be some limitation on the rental car itself. So it might be, you know, a lot of times it's up to 1,000 miles, and then after that, we're going to start charging you. So whatever it might be, we could say that 0 is a lower bound for t, and let's maybe just make one up to 1,000. Again, if you said just all positive numbers, that's also okay. This is what we call inequality notation. And you could use this less than or equal sign here as well to denote this. An equivalent way to note this would be using interval notation, which is using these brackets here. The closed, the square brackets mean closed, meaning it includes those values. So that'd be like both of these being less than or equal to. If they were both open or not inclusive, we say, we'd use round brackets. Okay, so these two things are equivalent. And then there's also set builder notation, which you might see something like this. T, the set of t such that, you know, t is greater than 0, t is less than 1,000. It's usually a set of elements such that, and then these conditions are met on the other side. These things are all equivalent. Okay. So this is for the domain. Now for the range, what's allowed? That means the set of possible outputs. So what costs are we expecting? Well, I haven't said that there's any upfront cost, but there might be a fee to begin with, right? And, you know, there's going to be some maybe maximum on the cost that you'd pay, but maybe not. So, you know, we could see something maybe like there's a cost of 0 up to, you know, $500 before you have to turn it in. Who knows? Or that it could be up to positive infinity. You could just pay for this car infinitely. Doesn't quite make sense, but again, the bounds of this example are not super well defined. The goal here is to really just think about it and talk through what the possible sets here are and to get reacquainted with this notation. Again, maybe 0 to 500, something like this for interval notation. Okay, so it's a verbal description. We're mapping it to some interval and inequality notation for describing the sets. Now let's take a look at a different perspective. Okay, let's look at the graphical. So I have a graph here, a completely different function. Okay, this is not the cost function anymore. We want to describe what's the domain and range. So now again, shifting our perspective. What's the set of possible inputs? What's the set of possible outputs? Well, inputs are along the x-axis, right? So what possible inputs are being fed into this rule that's been graphed? Well, we see that the lowest x value or input is here at -3, and the highest one is at +2, and then it stops, right, left to right. That's our input dial. So we could say from here to here, right, is our set of inputs. You also notice that this is closed and this is open, meaning it's including the point on the left and not on the right. So maybe we could do something like this and say, all right, my domain is from -3 to 2, open there. Another way to describe that would be that I've got -3 is less than or equal to x, which is strictly less than 2. Both of these are possible domains. Let me actually pull this up here then. Okay. And now the range is similar, but with the output. But again, we're going between the maximum and minimum possible outputs. So what would that be? Well, we have a lowest output here and a highest output here. We see it ends up at this output of 0, but really the range is the full set of all things it could have been, right? So it's kind of how far up your pencil went and how far down your pencil went when you sketched this graph is one way you can think about it. So from here to here, this is your range. And it includes both the top and bottom values. So we see that the range goes from, what, -5 up to 4 and includes both. Or you could think of it as -5 up to 4 like this. Okay, so this is the graphical perspective. Obviously, graphs can get more complicated than this, and so they'll need to be considered, but this is the basic idea here. Okay. Lastly, looking at the algebraic take on the domain and range of functions. So when we just have the formula, let's say you don't have a graph or you don't have a verbal description of something, you're going to need to do this by manipulating the equation. So there's a few things, and I've chosen these two examples specifically, is that you're on the lookout, again, for things that aren't allowed. That usually helps you inform what things are allowed, right? What's not allowed in the set will tell you what things are allowed in the set, okay? That's a common mathematical idea. So let's focus on this one first. What is not allowed in a square root function? Well, we know that you can't take the square root, doesn't allow x to be less than 0. We can't have negative numbers inside there. So this is something that we base this idea on. So then for this particular function this means that the inside here, whatever it is, in this case 2x minus 1. Sorry, my dogs love domain and range. So this means that 2x minus 1 has to be greater than 0, right? Take a moment and realize that that has to make sense, right? This value, 2x minus 1, for whatever values x takes on, can't be negative. If it does get negative, we're taking the square root of a negative number, and that breaks the whole thing. So then this must mean that 2x must be greater than 1 if I add 1 to both sides, which then means that x must be greater than a half. Okay, so what I just found is the set of possibilities for the inputs, which is the domain. Okay, so here this tells me that the domain is, we could do like this, 1/2, and it can be 0 on the inside. So we could say x can be greater than or equal to 1/2, and up to infinity can be anything beyond that. Okay, so that's my domain. Range, what can my range be here? Well, similarly, what you want to do is find the lowest point that you can get with the output, which here would be 0. If you let x be 1/2, that would drive this down to be 0. And then over time, this function will increase without bound. And you can see this just by graphing it. I'm not going to do that here to save time, but we see that the range is actually from 0 to infinity as well, or 0. Okay, and that's for this first one here. And so for square root functions, this is something we commonly look out for. Now, how about when we've got a rational function here? What are things we have to look out for when we've got a rational function? Well, you need to look out for the denominator can't be equal to 0. Right? So we're these are the two main things we've been on the lookout for all this time, K through now, is you can't take the square root of a negative and you can't divide by a 0. Those are the limitations in math so far. So what does that mean? If I'm looking for the possible set of inputs, and I'm just going to find the domain for this one and not the range. You can graph it to find the range. The domain here is only what doesn't cause that to happen. Everything else is okay, right? So domain can't allow the denominator to equal 0. So what does that mean? It means that x squared minus 3x plus 2 cannot equal 0. So we're going to restrict the x values to not allow that. So then that means we need to go find what values make that happen so we can dodge them, right? What things cause the problem so we can avoid the problem. So here we can use our basic factoring techniques of x minus 2 and x minus 1 to solve this equation. So we'll ask, which x's cause this then? And so we'll see then this implies that x equals 2 or x equals 1 cause this issue. Excuse me. Or x equals 1 cause the issue. And I'm writing this in concretely because I see a lot of students work through this and then say the domain is x equals 2 or x equals 1. It's like, no, that's not the case. What happens with x equals 2 and x equals 1 is that it breaks the function. So it's really any inputs are allowed except for these two values. So what this tells us is that the domain is the set of x values, and you can use this notation. X is a member of the real number. You don't have to use this, but I'm just writing it here. X is the member of the real numbers where x is not equal to 2 or x is not equal to 1. Or you can say, I'm kind of running out of room here. Or you can say the domain is all real numbers except x equals 2 or x equals 1. So you can describe the set verbally. Or you can use interval notation. So you could say you can go from negative infinity up to 1 and not use 1. Union that with, which means join together with the interval from 1 to 2, not use 2, and then go from 2 up to infinity. So this is commonly used in your online problems to feed to the computer because it can read this a lot easier than it can read this. And so all that means is really on the number line, you're using all the values up to 1, skipping 1, skipping 2, everything else is allowed, which is exactly what we just kind of made sense of, right? So those are the kind of 4 perspectives on domain and range of functions. You're going to use these in a bunch of different examples to kind of drive these points home before we then take this into the next set of review concepts, which is average rate of change, how graphs behave in the short and long run. But first, we need to just get our heads around what's allowed inside a function and what does a function spit out. Okay, so have some fun. We'll see you in the next one.